Y acá si ahorita te voy a hacer señas. ¿Vale?
Así es. ¿Listo?
Ahorita te voy a
Okay.
¿vale?
So, hello, good morning, everybody. We are ready to start with our last session of this CART 2024. And then I will like to introduce our speaker. So I like to invite you to see the next. So thanks again to be here. So it's a pleasure for me to introduce our friend Juan Carlos Valenzuela from the University of Cadiz. And as usual, you can check, you can read his CV in our page and it's public information. So I like to talk about our friendship with Juan Carlos. I met Juan Carlos many years ago in a very, very nice conference that he organized in Andalusia in general, in the south of Spain. The name of this conference is Encuentro Andaluz. And the first time that I saw Juan Carlos, he looked very serious, very formal, because he's organizer, so he has to have all the time he's running and nervous, etc. But this summer, fortunately, I have to be Juan Carlos in a conference in Poland. He was a speaker in this conference, and he looks very relaxing. No problem. Then we have many, many times to talk. We drink wine, of course. We have very good eat. Polish and Spanish too, because, okay, he was serious and formal during the conference, but he always has time for a good dinner or a good lunch. And I like a lot the conference of Juan Carlos in Poland, not only me, all the organizers of CART was in Poland in this conference. So we decided to invite to Juan Carlos. We are sure that we will enjoy your talk, and we hope you will be part of the big family of this CART. So thank you, Juan Carlos. I will stop to share my screen, and then you can do it.
Thank you very much, Rita.
I don't know how to put this. Okay, another way. I don't know. Okay, the content something. Stop. Thank you, Juan Carlos.
Thank you very much. I don't know if you can see the slides because I'm not usual with this platform of Zoom.
We can see.
Yes. So first of all, I would like to say thank you very much for this nice presentation, and also want to thank the organizer to give me this opportunity to participate in this edition of CART. And of course, I would like to become a member of this great family from now on, if it will be possible, of course. Well, and the problems I would like to tell you today is I will give some introduction of some first results about problems related with domination, both in the framework of classic graphs, and also I would like to give some small introduction to this kind of problems in the context of fuzzy graphs. Let me start with by saying that part of this work has been published in the bulletin of the Iranian Mathematical Society. And the second part related to the FASI graphs is still under review. I have divided this talk in two main parts. The first one devoted to domination in general, to K-domination in general graphs, and the last one regarding to this new point of view in the context of FASI theory. Well, let me start by recalling some basic concepts that involve the domination theory. We say that a set D is a dominating set in a graph if every vertex outside this set has at least a neighbor in the set D. For example, in this case, the blue vertices are a dominating set because, well, it is clear that every vertex outside this set is dominated by one of the vertices V1 or V2. And a total dominating set is a variation of this concept in which we require that not only the vertices in the vertices outside the set D must be dominated, but also the vertices in D must be. So in this case, it's the same that if we require that the induced graph by the vertices in D must not have isolated vertices. So as in this case, these four vertices, become a total dominating set because any vertex in the graph is dominated by one of the vertices inside the set. The minimum number of vertices in such a set is known as the total domination number, and we use the notation gamma for the domination number and gamma t for the total domination number, as usual. Well, there are hundreds of papers in the literature that study these kind of problems, and one could ask what happens if I don't need to dominate the whole set of vertices in the graph, because in some sense there are vertices that are self-dominated. For example, in this case, if the green vertex is in some sense self-protected, we only have to find a set of vertices that dominates the remainder vertices in the graph. Well, in this case, the domination number for the whole graph is 3, but if we do not consider the green vertex W, we need only two additional vertices to dominate the graph. This is somehow related with the concept of Roman domination that was introduced by Cocaine and et al. At 2004. And this problem was based in a defensive strategy of the Roman Empire, in which, we can consider that the cities are self-protected, strong or undefended cities, such that any unprotected city must be defended by a strong neighbor. Or whatever, we can say that a strong place it is able to send a legion to an undefended place without leaving undefended the own place. This is formally conducted as a function, a labeling of the vertices of the graph with labels 0, 1, and 2, such that the condition that we are requiring is that any vertex with a label 0 must have at least a neighbor with having a label 2. For example, in this case, which is the previous example, we can give this labeling of the graph. And of course, we have that any vertex with a label 0 is adjacent to at least one vertex with a label 2. Well, this is a simple example in which the Roman domination number will be 4. And we use the notation of gamma R of G for the minimum weight of such a labeling. The weight of a labeling, of course, being the sum of all the labels of the vertices in the graph. And one of the first things we can say is that there is a one-on-one relation between this kind of labelings of the graph, this kind of Roman dominating functions, and the set of collection of set of vertices V0, V1, V2. Well, I would say, I would like to talk about partition of the set of vertices, because some of these sets in some case may be empty. So I prefer to talk about a collection of subsets. And of course, if we consider a Roman dominating function, that is to say a labeling of the vertices with such condition, the set of vertices with a positive label, with a label 1 or 2, clearly dominate the graph is a dominating set, because the other vertices have label 0, but must be adjacent to some vertices, some vertex in the set V2. And another easy consequence that we can note is that we don't need to have any couple of vertices having label 1 and 2 joined by an edge, if we consider functions with minimum weight. Because if we have a vertex with a label 1, which is neighbor of a vertex with a label 2, we can clearly change this label 1 to a label 0, and this is still a Roman dominating function with with less weight than the previous one. So another important thing to have in mind is that any vertex having a label 2 must be at least one private neighbor. Well, a private neighbor is a vertex with a label 0, which doesn't have another neighbor in the set V2. And this is for the same reason that I commented before. Well, we also can define the concept of total Roman dominating function in a similar way. It is also a labeling of the vertices of the graph with labels 0, 1, and 2. But in this case, the set of positive labels induce a subgraph which have not isolated vertices. That is to say, any vertex with a positive label must have at least a neighbor with a positive label. In this case, as we can see, we have a total Roman dominating function that have weight 6. And we use the classical notation for this parameter. And we have a lot of results regarding the relation between these two parameters. Clearly, the domination number is less than or equal to the total dominating number, because any total dominating set is a dominating set. And one of the most well-known inequalities regarding these two parameters and the Roman domination is that the Roman domination parameter is always between the domination number and twice the domination number. of course, there are a lot of results that provide bounds relating all these domination parameters with the Roman domination and total Roman domination. And from the original paper by Cocaine, we have several other variation of these problems. In the literature, we can speak about weak Roman domination or signet, restrained, independent, many others. No? In this case, we're going to talk about one of these generalizations that is somehow related with the last one in this slide, the double Roman dominating number. Well, what is a double? What a double Roman dominating function is? If we recall the definition of Roman dominating function, in some sense, what we're looking is that one can send one legion from any strong city to any undefended city without leaving any city undefended. In this case, in the case of the double Roman dominating function, we label the vertices with labels 0, 1, 2, and 3. And the condition we are looking for is that one can send to any undefended city, not one legion, but in this case, 2 legions to defend this weak city. Yes, it's quite similar, the definition, to the Roman domination function. And as we can say in these examples, if we give to the central vertex, in this case, the label 3, it is possible to send 2 legions to any other undefended places without leaving undefended the original city. And also in the graph in the right side, to any vertex which have label 0, we are able to send 2 legions from its neighborhood without leaving undefended any of the original places. Well, in this case, as in the case of the Roman dominating number, we consider the minimum weight of such a double dominating function, and we call this parameter the double Roman dominating number. There are also a lot of papers studying this problem and studying the relation with the original one. And in one of these papers, we introduce some kind of generalization in which we consider labelings of the vertices with labels from 0 up to k plus 1. And in this case, we require that we are able to send to any undefended place. We are able to send k units, k legions from the neighborhood to any undefended place. Formally, we can define this as a function such that the value of the weight of the close neighborhood of any vertex must be at least k plus the number of active neighbors of the vertex, such that if the function satisfies this condition, we are able to send k units to any vertex in the graph without leaving undefended any of the original places. Here you have an example. If we have a vertex, like the blue vertex with a label k minus 3, we have to be able to send to this vertex from its neighborhood at least 3 units. And we can do it from the vertex with label 3 and the vertex on the right side. We can send another one so that we are able to send to this vertex k legions if we use the original Roman domination notation. Well, the first question that one have to one have to answer is if the transformation of from Roman domination into K-Roman domination is trivial, and it is not difficult to see. It is not difficult to see that if we consider a Roman dominating function like this one, it is automatic to consider a K-Roman dominating function in the graph by, changing the labels 1 by label k and the labels 2 by labels k plus 1. Clearly, we obtain a K-Roman dominating function, but this is not minimum because it is possible to find another labeling of the graph with less weight. So due to this fact, we consider that is interesting to study this problem because the transformation from one model to this new one is not trivial. Well, clearly to calculate or to study the exact value of this parameter even for very simple graphs is not easy. So we started working into fine bounds, upper bounds and lower bounds that permit us to consider an estimation of this parameter in some kind of graphs. The first result that we prove is a very easy upper bound. It's not difficult to prove that the inequality holds. If we give to any vertex in the graph this label, we have the inequality. And well, also we have proved that the equality hold only for the K2 graph. Clearly, I will show some sketch of the proof because it's not difficult. Is if we consider the graph K2, it is very easy to check that the K Roman dominating number is K plus 1, which match the value of the bound. And in the other hand, if the equality holds, well, it is not difficult to study some cases. For example, if we have in the graph a support vertex and a strong support vertex, we can label in the vertices of the graph in that way. If we have a weak support vertex, then we can label the whole graph in that way. And of course, if the minimum degree is 2, we can label in that way such that in any case, we can obtain a K-Roman dominating function with weight less than the minimum, which is impossible. So it's one first easy result. And another aspect we study is the complexity of the problem, of the associated decision problem. In 2021, it is proved that the triple Roman domination is NP complete. And also some years later, it is proved that the same holds for the K-Roman domination, the general problem in the case of bipartite and chordal graphs. And recently, for star convex and convex bipartite graph, it is proven that the triple Roman domination decision problem is also NP complete. So we have extended this study to the case in which we are working by proving that the general K-Roman domination decision problem is also NP complete, even for star convex and convex bipartite graphs. I would like to give you also some ideas of this proof because it's quite larger, but it is interesting to, it is interesting to understand the idea of this proof. We have related this problem with the 3-SAT problem, which is a well-known NP-complete problem. And to do that, we have constructed a bipartite graph, in this case, a star convex bipartite graph, by using some kind of gadgets that we relate with the elements of an instance of the 3-SAT problem. If we consider an instance of the 3-SAT problem, for any element x, y of this instance, we add this gadget that consists in a couple of vertices, xy minus and xy plus, and then we add the two sets of k plus 1 vertices, the y vertices and the z vertices, such that the first one are all adjacent to the central vertex, and the vertices set are adjacent to both the couple of vertices xy minus and xy plus. Well, by adding a gadget for each vertex, for each element in the clause, we can construct this graph by adding a new vertex t, which will be adjacent to every extra vertices xy minus and xy plus. And also, finally, we add one additional vertex for each clause, and we join these vertices to the corresponding elements in the clause. Well, once we can construct this bipartite graph in polynomial time, we prove that the instance of the 3-SAT problem is satisfied if and only if this star convex bipartite graph has a k Roman dominating function with a given weight. Well, we continue to prove some additional results, trying to, as I said before, to upper and lower bound the exact value of the parameter. And in the next one, we prove this upper bound, in which we consider a vertex with maximum degree. We give it the label k plus 1. And what we do is to assign the label 0 to any vertex in its neighborhood. In that way, if, well, it is clearly a k Roman dominating function because any vertex is adjacent to the vertex k plus 1. So the weight of this function become an upper bound of the parameter, and it is not difficult to compute this quantity, and we obtain this bound. No? So, well, this bound can be improved in some conditions, and if we modify slightly the conditions on the graph, we can improve the bound considerably. For example, in this case, if we consider a graph with girth at least 5, a minimum degree at least 2, we can decrease this label from k plus 1 to k, and also we can reduce the labels in the remainder vertices of the graph. In the previous result, we give to every vertex here the label k, and in this case, we can give to the remaining vertices this label, which permit us to obtain a better bound, because as the minimum degree is at least 2, we can assure that any vertex with a label 0 is adjacent not only to this vertex with label k, but also must be adjacent to another vertex with this label because the girth is at least 5, and so the neighbors of these vertices cannot be only the vertices with label 0. This permits us to obtain a better bound, and this bound is achieved in some cases. For example, for the cycle C5, we can prove that this is exactly the value of the parameter. Well, we also have some results that improve these bounds in particular cases. In the next proposition, we give an upper bound for regular graphs with girth at least 7, and which is tight for the cycle C7, and also for connected graph with minimum degree at least 3 and girth 7, we can improve a little bit the bound, and we can prove that this bound is better than the bound that the previous one in some cases. For example, for 3 regular graphs. Finally, another bound that we have proved, that we have obtained, is the one in this proposition, and it's a bound that well, the proof is based in probabilistic reasoning, in which we consider a fixed set of vertices M and a fixed value P that represent the probability that a vertex belongs to this set, and then we can estimate the awaited value of the size of M in terms of this parameter P. Well, after we apply some tools from calculus to bound this function by an exponential function, and we compute the bound minimizing this quantity. Finally, the last bound is an upper bound, sorry, a lower bound, which is much more difficult to prove that the upper bounds. In this case, we have used a discharging procedure to prove this bound. And well, an idea of the proof consists in giving some initial charge to any vertex in the graph. Well, we can consider a Riemann dominating function with minimum weight, and we can assign this initial charge as the label of the vertex. And then we apply this rule in which any vertex with label J sends some quantity to any neighbors in the set B0. Well, after some computation, we can assure that the final charge of any vertex must be at least this quantity, and this permits us to prove the lower bound. Well, as I said before, it's not too easy to find the exact value of this parameter, even for very simple families of graphs. What we have to do in the next results is to characterize the graphs, those graphs that have the minimum possible value of the parameter. In this case, the value of the k Riemann dominating number equal to k plus 1. And we also prove that there are no graphs. There are no graphs with this parameter equal to k plus 2. And also we have proved the exact value for the path in terms of the modulo 3 of the order of the path. Well, this is what I would like to say about k Riemann domination in this framework of classical graphs. And in the second part of this talk, I would like to extend this concept of domination, Riemann domination, to the context of fuzzy graphs. Well, many years ago, some authors introduced the concept of fuzzy theory, and other authors have studied this kind of graph regarding to classical problems like connectivity, coloring, or something like topological indices. And formally, a FATSI graph is a set of vertices and a couple of membership functions, sigma and mu. Well, sigma is called the membership value of the vertices, and mu the membership value of the edges, satisfying some condition, which is that the mu function must be a FATSI relation with respect to the function sigma. In other words, that means that the value of the membership of an edge must be at most the minimum of the values of the membership of its vertices. Well, in some sense, what we are going to say is that is logical that an edge exists in the graph if at least the two end vertices exist. It's not a contradiction. Well, in the framework of FATSI graph, we consider the concept of FATSI path is a set of ordered vertices and a set of ordered edges, such that the membership value of any internal edge is positive. We call the strength or the connectivity strength of a path as the minimum of the connectivity of the internal edges. And we say that an edge is an effective edge if it has the maximum possible membership value. Or that is to say, the value of the membership function for the edges is equal to the minimum value of the membership of the end vertices. And the main concept in this section is the concept of a strong edge. What a strong edge is? Well, we say that an edge is a strong edge if it is not possible to go from one end vertex to the other one by means of a path that have a connectivity strength greater than the mu value of the edge. Well, note that it's very easy to see that every edge in a path is a strong edge because well, there is no way to go from its end vertices other way than the edge joining it. Is the only way to go from one vertex to another one. So every edge in the path is a strong edge. And also every effective edge in a FATSI graph is a strong edge because, for example, in this case, if this edge is an effective edge, its value is the maximum possible value. So the strength of any other path should be less than or equal that mu of this edge and less than or equal mu of this other edge. Also, for that reason, the value of these two edges is at most the membership value of the end vertices of the edge, and therefore the edge is strong. Well, keeping in mind that every effective edge is a strong edge, we can see this example in which, blue labels are the sigma values of the vertices, and the red one are the mu values of the edges. And in this case, for example, the edge in the upper side is not a strong edge because the path joining the end vertices in that way have connectivity 0.3, which is greater than the mu value of this edge. So this is the only edge that is not strong in this graph, because I don't know, for example, any other edges is strong because the path joining the n vertices has a strength, connectivity strength 0.2, which is less than the membership value of the edge. But if we add, for example, this new edge, the edge in the left side, which was a strong edge before, now is not, because we can go from one n vertex to another one by this path, which have the connectivity strength 0.7, which is greater than or equal to is greater than 0.4. So this in this case, in this graph, this edge is not a strong edge. This is the difference between strong or not strong edges. Regarding this concept of strength or connectivity strength, some concepts are defined in the FATSI graph. In this case, the degree of a vertex is not like in a classical graph in which we have only one definition. The degree of a vertex is the number of edges that are incident with the vertex. In the framework of FASI graphs, we have many different definitions of the degree of a vertex. For example, we can talk about the degree of a vertex as the sum of the membership value of the edges joining this vertex with its neighborhood. But we can consider only the strong neighbors, and then we can define the strong degree of the vertex as the sum of the membership values of the edges joining this vertex with its strong neighbors. And also we can define the strong neighbors degree in terms of the membership value of the vertices instead of the membership value of the edges. And as usual, we can consider the minimum and the maximum of these three parameters, and we will use the classical notation for minimum and maximum degree, strong degree, and strong neighbor degree. Well, we also use this notation. Mu s of a vertex is the minimum value of the membership value of the edges that are incident are strong edges incident with the vertex. And we call the order the sum of all the membership values of the vertices. Then the size, in the similar way, we define the size of the graph by the sum of all the membership value of the edges. And we have to consider two different cardinalities: the usual cardinality of a set as the number of elements, and the scalar cardinality of a set, in which we sum not the number of vertices in the sets, but we sum the membership value of the vertices in the set. And finally, we define the complement of a graph in a natural way, the same set of vertices, and we consider the complement of the membership value of an edge with respect to the minimum of the membership values of the n vertices. Well, let me show you all this concept in this small example. In this case, we have 4 vertices and 5 edges. The neighbors of the vertex V2 will be V1 and V3. Of course, the degree will be 0.2 and 0.3, the sum of the values of the membership function for the edges. But as this edge is not a strong edge, the strong neighborhood of the vertex V2 is only the vertex V3. And of course, the degree will be 0.3. If we consider the other concept of strong neighbor degree, we have that this value is 0.9, which is sigma value of the vertex B3. In this case, the minimum value of the function mu is 0.3, which correspond to the vertex B3, and the maximum is 0.9, that correspond to the vertex B1. Well, this is a list of more or less the main concepts we have to use in this section. And keeping this in mind, some authors have studied and have introduced the concept of domination in some sense. The strong a set is a strong dominating set if every vertex not in the set is strongly dominated by D. That is to say, it has a strong neighbor inside the set D. And the difference is that some authors compute the strong domination number by using the scalar cardinality, that is to say, by summing the sigma values. And Sunita et al. Used a similar concept by computing the strong domination number by summing the values of the strong edges. We will introduce the concept of Roman dominating function in FATSI graph by using this last definition of the strong dominating number. Well, the difference is with respect to the classical graphs is that when we have a graph, we can define the Roman dominating function as a labeling with labels 0, 1, and 2. And in this case, we know that an edge belongs or not to the graph, so that we can compute the number of vertices with a positive label in a clearly way. But in the case of a FATSI graph, we have not edges that belong or not belong to the graph, but we have edges that have a more or less a probability of belong to the graph. So it's a little bit different to compute the value of this parameter. We in this case have introduced the concept of strong neighbor Roman dominating function. Basically, it's a labeling of the vertices of the graph with labels 0, 1, and 2, such that every vertex having a label 0 must have at least a strong neighbor with a label 2. It is important to keep in mind that it must be strong neighbor. So any vertex with a label 0 must be a strong neighbor dominated by a label 2. Well, in this case, we define the weight of such a strong neighbor Roman dominating functions as in a similar way as Sunita and other did for the strong neighbor dominating sets by using the sum of all the products between the label of a vertex and the corresponding value of mu s of this vertex. Of course, the strong neighbor Roman dominating number will be the minimum weight of such a strong neighbor Roman dominating function. Well, for example, if we consider this FATSI graph in which the blue labels are the sigma values, the red one are the mu values, and the green represents the labeling of the function. We have that in this case, this is this vertex has a label 0, and this vertex 1 here that have another 0 label should be a strong neighbor dominated by a vertex with a label 2. In this case, that's not happen because this vertex is not dominated, has not a strong neighbor with a label 2, because this edge is not a strong edge. So we have to be careful when we assign the labels to the vertex, because it's in somehow different to the classical parameter. But for example, if we consider this labeling, we assign to this vertex the label 1, and to this one the label 2. This will be a strong neighbor Roman domination function, and in this case, the weight of this strong neighbor Roman dominating function will be twice the mu value of this vertex, which is the minimum of these two values, 0.4, plus 1 times the value for this corresponding vertex, which is 0.3, so that this function has total weight 1.1. Of course, this is a strong Roman dominating function, but not this. It's not a function with minimum weight, because we could consider this other function in which we assign the label 1 to this vertex and the label 2 to this one. And in this case, this is also a strong neighbor Roman dominating function, because any vertex with a label 0 has a strong neighbor with a label 2. And in this case, the weight is twice 0.3 and 1 times 0.4, which is in fact is actually the minimum value, and this is the exact value for the strong neighbor Roman dominating number in this case. Well, after this introduction of the concepts that we have defined in this work, we have proven several relations of this new parameter with well-known domination parameters in fuzzy graphs, and as in the paper of the case Roman domination in classical graph, we have proven some tight bounds and some exact value for a specific fuzzy graph, but in this case it's even more difficult than in the previous case, because in fuzzy graph the things does not work as in the classical one, as we can see, for example, in this case. It is worth noting that if we have a classical graph, for example, this graph has a Roman domination parameter equal to n, but if we consider the corresponding fuzzy graph without strong edges, in this case, due to the fact that there are no strong edges at all, the weight of any strong neighbor Roman dominating function will be 0, even if the label of the vertices are not. So in fuzzy graphs, things go different than in the classical problem. For example, in this case, it is well known that for the classical Roman dominating parameter, for the hexagon, the optimum way of labeling the vertices is to consider two diametral vertices and give to them the label 2, the remaining vertices with the label 0, and this is the exact value for the case of the cycle of the 6 vertex. But if we consider the somehow equivalent fuzzy graph, and we try to use the same strategy, if we give the label 2 to these two diametral vertices, we obtain, of course, a strong Roman dominating function, but the weight of this function is 2 times the minimum of the strong edges incident with the vertex, which is 0.3, 2 times 0.3, 0.6, and the same for this vertex, twice 0.01, obtaining a total weight of 0.62. Well, in this case, we can consider this other labeling of the graph, in which we are using more labels, label 2, and label 1, but by using even using more labels, we obtain a strong Roman dominating function that have less weight than the previous one. This is in somehow anti-intuitive, because when I try to find an optimal function, we are always thinking in using the minimum possible number of labels, and also the maximum number of ones and the minimum number of labels too. But in this case, in the case of fuzzy graphs, this is not what leads us to the optimal function, as we can see in this example. No? We have this vertex 2, this vertex 2, and this vertex 1, but the total weight in this case is 0.34, because this new vertex with a label 2 has a strong neighbor which have a mu s equal to 0.01 instead of 0.3. So we must be careful with these kind of things, and we have to choose very well the labels we use to obtain the strong neighbor Roman dominating functions, because it's not so intuitive that compared to the case of the classical graphs. Well, we have proven some general results in this first work. Our first result is a chain of inequalities very similar to the one given for the Roman domination number in classical graphs. And the proof is quite similar, so I will not repeat the same reasoning that in the general case. Basically, we consider a minimum dominating set, and we give to these vertices the label 2, and we compute this is of course a strong Roman dominating function, and we compute the weight of this function, and we obtain the bound. It's quite similar to the classical one. This case is a little bit different, but well, because we have to use the strong cardinality instead of the classical cardinality. So in the chain of inequalities, we introduce the sum of the mu s values of the vertices, but the result is really easy to obtain. And also we have characterized the graph that achieve the upper bound as an equality. In this case, we have proven that the only graph that satisfy this equality is the graph without any strong edge. It's not difficult to prove it. As I have said before, we have devoted this work to prove some results that permit us to bound more or less accurately the value of the strong neighbor Roman domination number, because it's really difficult to obtain this the exact value for this parameter. We have also tried to prove the exact value for some particular families of graphs. In this case, in this result, we have do it for the complete bipartite graphs. As you can see, it's not even easy to describe this exact value in terms of the cardinalities of the vertex classes. We also try to do the same with the cycles and paths. It's really difficult to obtain this exact value. We have only proved for the path, and we are still working in the cycles. And I think that this is all I would like to say you today about these Roman domination type problems. Thank you very much.
Ay, un segundo que no me puedo. Oh, okay, thank you. I have
I
problems.
thought that I was alone.
No. I have problem to put the camera and the sound. So thank you very much, Juan Carlos, for your talk. I think that it is very interesting for our students to see that many things. For example, if you change a little one condition in one problem, then you have a complete different problem. The complexity can be more strong or more easy in another case. And another thing is that sometimes to solve the same problem, but different case, we have to use different techniques. And I think that this is very important to our students to know this, that always is good to have many information of techniques. Yeah. So thank you very much. I don't know if somebody has a question, comment. Of course, in general, we have comments and questions later, so, but I don't know in this moment.
No.
No? Okay, so if no, I'd like to say thanks again to Juan Carlos. So let us to continue in 2 minutes. We will stop with transmission and we will start again in 2 minutes. So thank you very much.
Thank you very
The
much.
live transmission, you can stay in the same.